Hello, I am Hanka, Řada.
Hello, I am Štepán, Starosta, and we would like to present you the results of our article Bounds on the Period of the Continued Fraction after a Möbius Transformation. In our article, we deal with so-called Möbius transformations, which can be seen as a transformation associated to a non-singular integer matrix, ABCD, and the transformation transforms the input x to ax plus b over cx plus d. And the question we deal with is how does the period of a continued fraction of a quadratic number changes when applying such a transformation. And the basic tool we use for this task are so-called Raney's transducers, who introduced them in 1973 in this article.
So, if we, for example, want to compute a 1/3 of the golden ratio, so it corresponds to this transformation, we can use the Raney's transducer. For this case, the transducer looks like this, and we have the input word, which is equal to RL, and so on, which is the RL representation of the golden ratio, and we start in this vertex. At first, we read the first two letters of the representation of the golden ratio and go through this edge and get this output and go to this state, and so on, and we can see that after a while we have the output word, which is equal to this word, and it's periodic, and it corresponds to this continued fraction. So we can see that the transformed number has period equal to 2, and it's 2 times the period of the golden ratio. So in this time, the prolongation was 2 times.
So using these transducers and LR representations of numbers, we give a general upper and lower bound on what can happen with the ratio of the two periods of the input number and the transformed number. So x here in this theorem is the input irrational quadratic number, and hm of x here is the transformed number, and we are looking at the ratios of the periods. So on the right and left side we have the periods of the minimal periods of the input quadratic numbers of the continued fraction of the number x, and we give these bounds on the prolongation and the shortening of the period. And the bounds they are given by this ugly formula here, and where the important function which is inside the formula is denoted xi, which is the number of steps of the Euclidean algorithm of two coprime positive integers e and f. So let me give some examples of this formula. Here we have a table of some computer experiments actually showing that in some cases the bound is as good as it can be. It's a sharp bound. And here that's the determinant of the matrix associated to the Möbius transformation that we deal with. And we list here the upper bound on the actual prolongation, which is denoted pi n of x here. So this was denoted as n. Then the actual prolongation that we obtained for some x here. So x's are listed in the last column here. So as you can see, for some examples, we obtain exactly the upper bound as given by our formula. And for some rows, like this one, we were not able to obtain the actual upper bound, which is here 112. We only could obtain the ratio of 81. We can deal with this a bit better for prime n, where we can prove, say, a better formula, and we give more comments in the article on why this happens for some determinants n. Okay, so that's all for us. If you're interested, we hope you enjoy reading the article. Goodbye.
Goodbye.